Hello and welcome to Lesson 4, IPsec and its configurations. Internet Protocol Security, or IPsec as it's known, is a suite of protocols that facilitate secure data transfers across IP networks. A commonly used function of IPsec is a VPN, or Virtual Private Network, allowing a branch office or telecommuter to access corporate resources from across the Internet. IPsec is a dual-mode, end-to-end security scheme. A key point to consider when working with IPsec is the two operational modes supported, tunnel mode and transport mode. Tunnel mode, as viewed in this graphic, is the most common. In tunnel mode, the entire IP header and payload data are encapsulated, and a brand new IP and special IPsec header are prepended. This new special header is referred to as the ESP, or Encapsulating Security Payload header. In transport mode, only the payload data is encrypted, leaving the original IP header unchanged. In this section, we're going to explore the main protocols and services supported by IPsec, and we'll take a look at a few ways to configure IPsec in a working VPN design. So what are VPNs, and why do we need them? VPNs, or Virtual Private Networks, allow organizations to establish working extensions to their private networks. These extended network connections allow secured access to specific resources, typically hidden outside of the campus infrastructure. Now, IPsec, while one of the more popular suites for accomplishing VPNs, is not the only game in town. Other common tunneling protocols include Microsoft's PPTP and the Microsoft Cisco jointly developed L2TP. Some key terms that come into play when discussing VPNs are intranet, extranet, and remote access VPNs. An intranet refers to a secured private network in which the users are fully trusted. A simplest example of an intranet is a branch-to-home office connection secured by IPsec across the Internet. This kind of connection can save an organization money when compared with a dedicated lease line or TDM circuit. Another example of an intranet might be an organization's secured web portal where employees can review their company benefits packages, access corporate training resources, or view a company directory. An extranet refers to a secured private network in which the users are partially trusted and are typically considered business partners. An example of an extranet is a manufacturer that will create a special zone for posting parts lists and assembly guides not directly available to consumers. Retailers and resellers can establish secured access to this data through what is known as an extranet. Another example of an extranet might be a hospital that creates a special zone for communicating with doctors, clinics, and labs that are external to the hospital. A remote access VPN refers to a secured private network in which a single trusted user, typically an employee, can get access to internal resources that are not visible or available outside of the corporate infrastructure. An example of this kind of VPN might be a traveling salesman or corporate executive that spends a great deal of time on the road and needs reliable secured access to corporate resources. Now, for a communication channel to be considered secured, it must provide three basic attributes. There has to be a mechanism to provide authenticity. We have to be sure of who we're communicating with. And there has to be a way to ensure the integrity of the data. We have to be sure the data hasn't been altered in any way along the path. And there has to be a mechanism to support confidentiality. The data has to be private and unviewable by anybody other than the intended recipient. A network layer protocol that supports these challenges is IPsec. IPsec is a dual-mode security scheme that operates at Layer 3 of the OSI, Open Systems Interconnection reference model. The IPsec protocol suite provides end-to-end security and has mechanisms that support authentication, data integrity, and confidentiality. Typical configurations incorporating IPsec are host-to-gateway, and gateway-to-gateway topologies. IPsec has become the de facto standard for establishing VPNs. So IPsec is a successor of the ISO standard NLSP, Network Layer Security Protocol. NLSP was based on the SP3 protocol that was published by NIST, the National Institute of Standards and Technology, but designed by the Secure Data Network Systems project of the NSA. These security schemes were formulated due to the inherent security flaws within the IP4 version of the protocol. IPsec is considered an add-on to IP version 4. However, it was built as an integral part of IP version 6. One of the key differentiators of IPsec and higher layer security schemes is when protecting application data with higher layer security schemes, the application must be aware of the intricacies of the API. When protecting application data with IPsec, standard universal APIs are usable. By establishing secure channels between endpoints rather than applications, there is a significant portability within the design. There are three different architectures or implementation models defined by IPsec: the integrated architecture, the bump-in-the-stack architecture, and what is known as the bump-in-the-wire architecture. Although a tightly integrated architecture is always desirable, it's not as common. In most scenarios, IPsec is configured using the bump-in-the-stack or bump-in-the-wire model. With the bump-in-the-stack technique, IPsec is made as a separate architectural layer between the IP or network layer and the data link layer. The advantage of this technique is that IPsec can be retrofitted to any IP device. The disadvantage is that there is a duplication of effort as compared to the integrated architecture. Additionally, there is a need to alter and/or install IPsec drivers into the endpoints. Bump-in-the-stack is generally used for IP version 4 host-to-gateway and host-to-host topologies. With the bump-in-the-wire method, a hardware device that provides IPsec services is placed between entities. The advantage to this architecture is there is no need to alter and/or install the IPsec drivers into the endpoints directly. The bump-in-the-wire is generally used in an IP version 4 gateway-to-gateway architecture. So let's take a closer look at how an IPsec VPN is established. A key concept to understand here is the process known as handshaking. The term handshaking comes from the notion of an agreement, which is in fact what's going on here. Since IPsec has several possible services, algorithms, modes of operations, and protocol options, the endpoints must agree which of these to use, and they must agree or a VPN cannot be established. Once an agreement is made, a security association, or SA, is created and stored on each of the endpoints in a small dynamic database called a security policy database. The SA, as we'll discover later, becomes a critical aspect of the VPN and is used to associate incoming traffic with the VPN agreement. IPsec can be configured manually or by using an automated key management protocol, such as IKE or Internet Key Exchange. In manual IPsec, the security association attributes are configured manually on both endpoints, and there is a need to communicate those attributes to one another with some form of out-of-band method. The de facto for automating key management in IPsec is through what's used as IKE, or Internet Key Exchange. You could think of an IPsec VPN configured with IKE as being two tunnels, one inside of the other. The first tunnel, or outer tunnel, is negotiated to establish a secure channel inside of which a second handshaking process takes place securely. The goal of the second handshaking process is to establish a symmetric or shared key that can be used to assemble and disassemble data in and out of ciphertext. To ensure the symmetric key is kept secret to everyone but the VPN partner, the handshaking and agreement are done securely under the protection of the first or outer layer tunnel. It happens that these two processes are referred to as Phase 1 and Phase 2 respectively. Phase 1 is used to establish a security association between the endpoints and builds a secure channel that allows the inter-tunnel agreement to take place. Phase 2 is used to exchange keying material known as a session key. Like the Phase 1 process, the Phase 2 process also has to meet with a full agreement in order for a VPN to be built and remain functional. In manual IPsec, there is no concept of a phased handshake process taking place. The options are static and therefore inflexible. As notable in this graphic, the only attributes that are configurable in a manual IPsec VPN is the pre-shared key and a limited choice of authentication and cryptographic functions. A VPN built using manual IPsec will have to be built statically and is weakened due to the persistent nature of the session key. Additionally, this IPsec variant is inferior due to the lack of asymmetry in the keying process. The protocol is extremely vulnerable to brute force attacks. The good news is that manual IPsec is rarely deployed, but it is something that you'll still find in existing legacy VPN topologies. You may find yourself cleaning it up or migrating off of it, and for that reason an understanding of the protocol is crucial. In this graphic, a Juniper firewall is configured for manual IPsec using ESP and the AES 256 scheme. Note the key can be either entered manually or generated using a passphrase. The VPN peer must be configured identically. Hence, the key and/or the passphrase will have to be communicated in an out-of-band method to the VPN peer. This, of course, increases the risk of compromise and creates a long-term scalability issue. The lack of security and poor scalability drove to the creation of the Internet Key Exchange, or IKE. IKE exists to allow two endpoints to securely and asymmetrically set up a security association. IKE uses the ISA-KMP or ISAKMP, Internet Security Association and Key Management Protocol, as a framework to support the establishment of a security association compatible with both endpoints. IKE uses Oakley as a protocol that supports two authenticating parties agreeing on a secure and secret keying material. The basic mechanism is Diffie-Hellman. Diffie-Hellman is an asymmetric method of exchanging a symmetric shared key asymmetrically. This is typically stacked during Phase 1, but can optionally be added during Phase 2 using what is known as perfect forward secrecy. Once the initial session is derived asymmetrically, there will be a rekeying interval established, and during this interval, new system-generated session keys will be communicated securely using the SA derived during Phase 1. At a less frequent interval, the asymmetric Phase 1 process will also perform a rekeying process. In this graphic, you can see the automation associated with an AutoKey IKE session. Observe that during Phase 1, a security association is built using an agreed-upon pre-shared key. Once the SA is established, Diffie-Hellman is used to initialize a session key asymmetrically. Phase 2 happens and data transfers can begin, assuming a successful handshake has occurred between the endpoints. Rekeying occurs periodically using the existing SA created in Phase 1. The typically configured Phase 2 rekeying occurs about once an hour. Phase 1 will rekey on a less frequent interval, typically once per day. In IKE, there are two possible modes of operation. Main mode, in which there are 6 messages exchanged between the endpoints, and aggressive mode, in which there are only 3. In main mode, the first 3 messages that are sent with an offer by the initiating peer, and the remaining 3 messages are a response to the peer's capabilities. Main mode also makes it possible to configure multiple capabilities on the gateway, allowing for a wider range of VPN peering. Aggressive mode, in which there are only 3 messages exchanged, the initiator sends the 3 messages with its capabilities, and the peer can either accept them or refuse them, and in which case there would be no VPN built at all. Main mode is the most commonly used in a gateway-to-gateway VPN design. Aggressive mode, on the other hand, is seen more often in host-to-gateway designs. The reasons for this is the typically dynamic nature of a host-to-gateway configuration in which very little information is known in advance about the host when configuring the gateway. In this graphic, a Juniper firewall is configured with multiple Phase 2 attributes, making it capable of supporting a wider range of VPN peers. So at this point, What happens when a gateway supports multiple peers with separate SAs for each VPN? A value known as the Security Parameter Index, or SPI, is an identification tag that is added to the IPsec header. This tag helps the kernel discern between traffic streams where different encryption rules and algorithms may be in use. The SPI is an essential part of the IPsec SA because it enables the receiving system to select the SA under which the receiving packet will be processed. An SPI has only local significance since it's defined by the creator of the SA. You could think of an IPsec SPI like you would port numbers in TCP and UDP connections. So, in this graphic, a VPN endpoint is configured with multiple active SAs. Unique SPI values are used to associate incoming VPN traffic with the correct SA. In this graphic, a sonic wall firewall is configured for manual IPsec. As we know, keys are manually configured in manual IPsec. But what's notable here is the incoming and outgoing SPI values. It happens that there are literally two IPsec SAs created for a bidirectional VPN tunnel. The SAs are directional and necessary in order to keep both send and receive data flowing. There are two basic services provided by the IPsec specification: authenticated header and encapsulating security payload. Authentication header is a key protocol in the IPsec architecture. It's used to provide a connectionless integrity and data origin authentication for IP datagrams. It also has provisions for protection against replays. In addition to origin authentication, authenticated header also provides data integrity through the use of integrity check values, ICVs. The ICV is calculated by passing the key from the Security Association SA and the entire IP packet, including the authenticated header and the algorithm identified as the authenticated header SA. The ICV value is then copied into the authentication data field. The resulting ICV is referred to as a Message Authentication Code, or MAC. Authenticated header may be applied alone or in combination with ESP. The second and more common service under the IPsec specification is ESP. ESP may be used to provide the same security services as AH, and it also provides the additional protection of data confidentiality. ESP is all about data confidentiality, while also providing origin authentication and data integrity. If authentication has been selected, the receiver computes the ICV over the ESP packet minus the authentication data using the specified authentication algorithm and verifies that it is the same as the ICV included in the authentication data field of the packet. Again, the resulting ICV is considered the MAC of the encrypted datagram. The primary difference between the authentication provided in the ESP and AH services is the extent of the coverage. Specifically, ESP does not protect any of the IP header fields unless those fields are encapsulated by ESP. As stated earlier, a key point to remember when working with any type of VPN is that both sides have to agree on the services and proposals in order to successfully bring up a VPN connection. On the next couple of slides, we'll review flow diagrams that present the decision tree in building a successful VPN. In this flow diagram, an endpoint is configured with a bump-in-the-stack design. A security policy database is shimmed in the TCP/IP stack between the IP addressing layer, layer 3, and the link layer, layer 2. The packet is passed through the security policy database, and based on the destination field of the packet, a decision as to whether it should be sent through the VPN or bypassed and sent out in the clear is made. During that decision process, the SPD will decide if the IPsec services are needed and whether they should be ESP or authenticated header. If the decision is to use either IPsec service, then the packet is encapsulated and forwarded to the lower layer protocols for transmission. If the VPN design is configured for what is referred to as a split tunnel, packets that are not associated with any IPsec services can be forwarded to the lower layer protocols in the clear. However, if the split tunnel functions have been configured as disabled, packets that are not to be serviced by IPsec are dropped. Split tunnel configurations are typically seen in host-to-gateway VPNs where an administrator wishes to add the additional security of blocking internet access to an endpoint while the VPN tunnel is in use. In this diagram, we can see the decision logic is associated with the recipient endpoint. When the frame is received by the endpoint, the initial link layer headers are stripped and the packet is examined to see what transport layer services are requested. If the next header, AH or ESP, is then been specified, processing will take place to ensure that the SPI points to an existing SA and that all of the ICVs are intact. If the packet is able to pass this process successfully, it is routed back through the same flow process with the IPsec headers stripped. Now the packet is treated like any other clear text data and sent to the upper layers of the stack. It's important to consider the layer-to-layer communication aspect when thinking about IPsec. The services offered by IPsec ride directly on top of IP and are parallel to TCP and UDP. Hence, ESP and AH are IP protocols and not TCP or UDP port numbers. For example, TCP is considered IP protocol 6 and UDP is IP protocol 17, whereas ESP is IP protocol 50 and AH is IP protocol 51, respectively. So in a nutshell, through the capabilities of its primary services, AH and ESP, respectively, provides both authentication and encryption for secure data transfers. This completes our discussions on IPsec. In this section, we've learned that IPsec is a suite of protocols and components, and we reviewed two of the operational modes of IPsec, tunnel mode and transport mode. We also learned of the two primary security services, authentication header and encapsulating security payload, ESP, that are supported by IPsec. We learned how IPsec supports the three primary requirements of a VPN, authentication, integrity, and confidentiality. And we saw how IPsec can be configured in a manual way that is both inflexible and vulnerable to certain attacks. We explored the challenges associated with key management and the need for a scalable, automated method of transmitting security keys to VPN peers. We took a close look at the Internet Key Exchange, IKE, as a solution to the key management challenges. In our next lesson, we'll explore the Open Systems Interconnect, or the OSI reference model. Thank you for viewing.